Our second talk is from Shunsuke Saito from Meta. And the talk name is Digital Human Modeling with Light. So first, please allow me to introduce Shunsuke a little bit. Shunsuke is a research scientist at Meta Reality Labs Research in Pittsburgh. He obtained his PhD degree at the USC. Prior to USC, he was a visiting researcher at the University of Pennsylvania in 2014. His research lies in the intersection of computer graphics, computer vision, and machine learning, especially centered around the digital human, 3D reconstruction, and performance capture. His work has published in SIGGRAPH, SIGGRAPH Asia, NIPS, ECCV, ICCV, and CVPR, two of which have been nominated for CVPR Best Paper Award at 2019 and 2021. His real-time volumetric teleportation work also won Best in Show Award in SIGGRAPH 2020 Real-Time Live. If I'm remember is correct, the name of the demo is Monopod. It's a very impressive demo. Okay, let's welcome Shunsuke for his talk.
Right. Do you hear me well?
Yes, very well.
And you see my screen, right?
Yes, we can see your screen. Yeah.
Awesome. Thanks for the introduction. It's a great honor to give a talk in this seminar. So today I'm going to talk about digital human modeling with light. Primarily centered at relighting, but I have some another thing to show as well. All right, so let's get started. So our Pittsburgh lab has been working on photorealistic avatars called the codec avatars. Our goal is to create like an authentic avatar that's indistinguishable from reality. It should move like us, look like us, and sound like us. And this is our latest demonstration shown in our Meta Connect 2022. Here, like two persons are like talking in real time through their volumetric avatars. And their avatars are relightable, so they can control their expression, but not only that, but they can also change their illumination condition. So like person hold their controller to move their like light around, and then the other person can see that in real time. So with that, basically, I want to first motivate why relighting is so important in this metaverse or telepresence. So here's a kind of side-by-side comparison with and without relighting. So if you put the person without considering the illumination, then this composition looks highly unnatural. And if you look at the right side, with the relighting, the person looks like the person is actually in this space, right? So so relighting definitely improves the immersiveness of avatars. So in this talk, I'm gonna first talk a bit about the capture system and the data, how we actually get this type of data. So our capture system is called MAGSI. So it's a multi-view capture system, and it consists of 160 cameras, 450 lights. And for non-relightable codec avatars, we just turn on all lights. And this MAGSI allows us to capture subject from many different angles, like you see on the left, with a various facial expression shown on the left. Okay. And what's more, this capture system is similar to light stage. I'm not sure in the video stream you can see it clearly, but we have a control of individual lights, and it's fully synced with the cameras. So by controlling those light patterns, we can collect different illumination conditions for each person. And let me first explain what we want to capture to actually enable relighting. So our multi-view capture system can observe the point X here from different viewpoints, as you can see here. And I plotted the observation point on the left. And if you also want to make it relightable, we also want to observe the point X under different light with a different light direction. So with this light direction, we want to see it from all the viewpoints and change the light, and we want to see it again from different viewpoints and so on. And this way, we can basically create our light transport metrics. Given the combination of light direction and viewpoint, we can reproduce how how the person look in this particular viewpoint and the light direction. However, like for avatars, this is not enough because like humans are dynamic. We actually move and speak and change poses, right? So that means this light transport is not only metrics, but actually a 3D tensor that also have a state. Because here state means expression or like a human poses. By changing the state, also the light transport tensor metrics will change. Okay. And so from now, I'm gonna constantly use this like a contrast between ideal and the reality. Usually, like first, let's start like what we want to get ideally and what actually get in reality. So ideally, this capture system provides this complete tensor. This way, we have like there's no like a job on top of it. We can just rewrite avatar from any expression. But in reality, what capture system gives us is just a bunch of holes in it. So it only gives us a partial observation over like a combination of light, illumination, and light expression and viewpoints. Because the capture system has a limited number of cameras and limited number of lights, and also like it's infeasible to collect infinite variation of expression in with a limited storage and also time. Okay, so and what we get is this time multiplex illumination. So over the course of time, we can change the illumination. So for each expression, we can turn different lights on and then like move on to different expression. That way we can correct all the variations. However, this requires the expression for each light condition. So it's left for our capture system with a 460 lights, it's roughly 460 times more capture time. This is apparently infeasible to do. So our solution is, given this limited observation, bunch of holes in this light transport tensor, we basically learn like a function through a neural network, and let the inductive bias fill in all the intermediate observations. So let me first talk about how we actually overcome this the cost of dimensionality. Okay, so one thing we propose here is a time multiplex dynamic capture. So instead of asking people to be static for each expression, we let just our person to have a arbitrary expression in time. So this way, so for every frame, we can change illumination and also expression at the same time. And this way, as you can see on the left side, we see more like an observation across different light condition and expression. So this basically increases the chance of getting the better observation of light and expression pair, but it's also still limited. And what we did in addition is to turn on multiple lights at the same time, not only one light, but 5 lights, for example. This way, for each time, we have an observation of expression and the multiple lights at the same time. In a traditional work, like decoupling all the light sources is challenging, but by combining it with a learning-based approach, like a neural network, we can actually also decompose the contribution of multiple light sources. I will talk about how we do this later. So this way, we can get basically 5 more lighting data for the same duration. All right. And another thing is a tracking, like how we get this state. So I mentioned that the state means expression, gaze direction, pose, and so on. And for the problem is so our a codec avatar system takes a multi-view capture system and run a 3D reconstruction, key points, and get the mesh tracking. That way we can build a high quality facial avatar called a codec avatar. However, in the relighting capture, as you can see, if you have only small lights on, then the part of the face is completely dark. It's really difficult to apply a traditional tracking with this kind of lighting frames. So our solution is to interleave free lit together with these partially lit frames. So here you can see that every 3 frames, we insert pre-lit, and then also we turn the other like 5 lights from the random direction for the intermediate frames. So this is how it looks. So as you can see on the left, every 3 frame is used for tracking because it's free lights on. And for the remaining 2 frames, we use it for learning a relatable avatar. So this is a kind of sequence, like every 3 frame, you see that there's always the full lights on, so we can reliably learn a tracking algorithm, and then we can learn interpolation to get their alignment for the relighting frames. All right, so that's the data on the capture system side. So let's talk a bit about the algorithm side. So our original codec avatar is presented in SIGGRAPH 2018. The idea is to basically auto-encode the avatar, the human's facial expression through an expression code and viewpoint with the variational autoencoder. As an intermediate representation, network spits out the geometry and texture, which is view dependent. And by combining them, you can render from arbitrary viewpoint with the different expressions. But this avatar is not relatable. So the naive extension of a relatable avatar is, hey, together with a viewpoint and expression code, what if we just condition the extra lighting information or lighting code? So the lighting representation here, just for the efficiency, instead of taking this high resolution environment map, we just downsample to 32 by 16. Okay. And for the training time, as I mentioned, we have a 5 lights on, right? So we can take this type of 5 lights on as a lighting code, and then let the network learn how their appearance look from all those 5 light combination. And then in the inference time, we basically replace that with the environment map, which we want to render the avatar with. And then we can hopefully relight the avatar under arbitrary illuminations. And ideally, given this limited observation, we can basically create this function to produce a photorealistic avatar and the different illumination, different viewpoints, and expression. And however, what happens is the generalization is a problem. If you have a limited observation, like if you don't pick a right inductive bias, network does not generalize well. Let me briefly talk about that. So the RE condition model, as I mentioned, like taking just all lights in a lat long image, this is difficult to generalize to Nobel light distance, because here we assume that the lights are like infinitely far and all light directions are same. But in reality, our capture system has a distance to the avatar, and also like if you put the lights close to face, the light direction varies depending on the location of face. So what we propose is called the light condition model. So instead of taking the light as a RE layer as the input of RE layer of the network, we insert the lighting direction as a later part of the network, so that it's spatially varying, so that it can account for more local change of light direction. And this is what we get. And this allows us to render avatars from arbitrary light conditions, such as this directional light to actually a near field light. As I mentioned, our capture system is like a dome, which actually has a 1 meter radius. But we can, in the test time, we can put the light much closer to face and still turn the avatar relightable with a realistic appearance, as you can see on the right side. And here's another problem. So there's a huge domain gap between the training data and the test, a test environment map. As you can see on the top, the light stage data give us this 5 lights on type of data. But in the test time, we want to basically relight the avatar with a more continuous illumination. And what you see here is if you just only train with this 5 lights on, the avatar does not generalize to produce realistic appearance under no illumination. So our solution is to leverage the linearity of light transport. Let me explain why it is. So we can decompose the target illumination as a combination of multiple point light sources, right? And if you have an observation of a person's face or anything under each point light sources, since lights are linear, meaning if you have a light one from one direction and there's another light from the other direction, the contribution of two lights are linear, so you can just simply add them up. So if you basically take a weighted average of a multiple observation, you can actually produce a novel illumination condition. This is called the linearity of light transport. If you change the illumination, so you can, although you only have an observation from just a single point light sources, you can still turn those like a faces under like different illuminations. And this is another extreme cases. Okay. And in our case, this all that observation is parameterized by neural network. So we take our late conditioned model to basically take this point light source and then turn this into a photorealistic appearance. And we can basically like take a weighted average of those. We can turn the avatar into our novel illuminations. So this allows us to generalize to natural illumination, although we only capture with those like light stage like point light light capture systems. Okay. There's another thing. So the speed is another important consideration for the digital human applications, because ideally we want to see the avatar in real time so that we can use it for communications. In an ideal world, this like neural network based relighting model is fast enough that we can render in real time. So that, for example, as a state, we can take from a headset images and then relight avatar based on the facial expression in real time through VR. However, this like if you take a linearity of light transport and then produce a novel illumination condition, it's actually too slow, because for each light condition, we have to run a neural network and we have to add them up. So simply, if you have a like 16 by 32 environment map, this means we have to run a neural network 512 times. This is far from real time. So our solution is to use a student-teacher framework. So let me explain what that is. So as I mentioned, the array conditional model is faster render because you can take whole environment map as an input. However, it needs a ground truth. Like as I shown earlier, if you only take those 5 lights on, it never generalizes. On the other hand, the late conditional model gives us the good generalization. It can render faces under any illumination. However, it's very slow. So what if we just take a late conditional model to produce a bunch of pseudo ground truths and then training this early conditional model so that we can render the natural illumination in real time. And this is called the student-teacher framework. So this allows us to render like faces in a more or less same quality with much faster rendering speed. But here on the left, you can see that our teacher model can produce natural realistic relighting results, but it's far from real time. And on the right, this is our distillated student model. With a more or less same quality, we can achieve 100 FPS. This is fast enough to render avatar through a VR headset. So from the camera stream from the head-mounted display, we can drive like our relightable avatar in real time, and we can preview it. Probably from online streaming, the video is a bit laggy, but hopefully you can see reasonable animation results here. Okay. All right, so we also extended the aforementioned pipeline to volumetric avatars. So these are the results shown here. We basically combined our volumetric avatar called mixture of volumetric primitive, which was presented in Asiagraphics 21, with our relighting algorithm. So this way, not only just a mesh-based avatar, but the volumetric avatar can be relit in real time with arbitrary illuminations. So here, in the middle, we show that we can put the light close to produce this near field lighting effect, but also we can turn the, like a volumetric avatar relightable in a natural illuminations, like you see on the right. So the quality of hair is significantly improved with a volumetric approach like NAF or like our own MVP. And note that MVP is highly efficient compared to NAF, and we can also render in real time. Right. So sounds like we solved everything, but it's actually not the case. So there's still a lot of things to be done. So let me also talk a bit about how we actually create more complete avatars with relighting. So there are a couple of limitations or the future work. One is articulation. So for body or hand, actually like humans are articulated. So we can change different poses, and still we want to relight avatar in real time with like a good generalization. The articulation poses extra challenges. Another thing is the composability. So if you have an avatar with accessory or like changing hair, but still like we don't want to lose the ability of relighting, right? This composition turns out to be non-trivial, and then we also propose a solution. So first, let's talk about the articulation. This work is like, so we worked on hand relighting in 2023, like it was published in CVPR 2023. So first, let me explain what are the challenges for relighting hand. The one issue is articulation, as I mentioned earlier. So if you change poses, then the shadow casted on the hand will change drastically. So there's an almost infinite combination of pose and illumination. The first, observing all of them is difficult. Second, like generalizing to all those combinations is difficult. So this is something we have to address. And another thing is interaction. So ultimately, like we don't want to only use a single hand for anything. We will interact with the object or the two hands. And this type of interaction is very common in a real world scenario, right? And we still want to relight hand under this type of interaction station. This also like cast a shadow on the other hand and so on. To achieve the good generalization, in our work, we propose a so-called neural relighting with a physically based lighting features. I will explain it a bit later. So first, let me explain what our data looks like. So as I mentioned, we use the interleaving time multiplex capture. So similar to face, every 3 frames, we have all lights on. And for other 2 frames, we use the pattern rich lights on. And then we use those remaining 2 frames for like learning a relightable appearance. And for this pre-lit frame, we use to learn the base geometry and the tracking. And here's our teacher model. So like we take local right direction, local view direction, and the shadow feature. For this taking shadow feature is really critical. On top of it, we want to create a pose-dependent effect such as wrinkle properly. That's why we also inject the pose information in the middle of the network. And this way, we can turn this shadow input, light direction, and so on into a photorealistic appearance of a human hand. And here's our results and the aberration study with and without shadow feature. And here, I'm going to flip between real data and our random model. So as you can see, the without shadow feature, it does not generalize to novel combination of light direction and the poses. And with our shadow feature, the network can still produce a photorealistic shadow under novel combination of novel condition of illumination and the hand poses. And what's more, even for like completely unseen light trajectories, our approach can successfully model realistic shading. And note that the important bit here is since we go through neural network to produce final appearance, the input shadow feature, for example, doesn't account for subsurface scattering and a more complex global light transport effect. But by combining this local light feature and neural network, we can still produce photorealistic appearance incorporating all the global light transport effect. And we can also render hand under a near field illumination, although we capture hand from like a 1 meter radius stone. So we can also change the light, not only direction, but also the distance. So still there remains a problem. We want to support environment map relighting in real time. So as I mentioned earlier, for FACE, we also apply the same idea of student-teacher, teacher-student framework. So OLAT model, just as a quick recap, OLAT or teacher model can generalize the novel illuminations by leveraging this linearity of light transport. Since we have to learn this the network multiple times to aggregate the contribution from different light sources, it's extremely slow. On the other hand, our student model can generalize well, but our student model is fast to render, but it needs a ground truth data. So we pair them up and then just supervise a student model. For the student model, the big difference from the face work is we actually take a lighting feature instead of just simply taking the environment map as a long, like a vector. So here, similar to some of the portrait relighting work, like total relighting, we compute the diffuse feature as well as a specular feature, given a coarse hand proxy. And here, the important thing is for hand, we incorporate the visibility. So without incorporating visibility, it does not account for the correct shadowing effect, especially if you have a multiple hands. So here's our results. Our student model can render hand in a reasonable speed. So this is a volumetric primitive-based hand model, and roughly the speed is 33 frames per second. It's reasonably real time, and we can render hand under natural illuminations together with correct shadowing effect. As you can see, when the light moves, there's a shadow moving around on the palm. So here's our ablation study and the comparison. Here on the left, I show our results, and in the middle, our result without visibility incorporation, and the rightmost is basically the adaptation of our area work of face as it is. So without taking this spatially varying light feature, no visibility and so on. So as you can see, without visibility condition, the network does not produce correct shadow and sometimes produce artifact. And also like just naive extension of our face work does not generalize well. So this kind of will justify the way we kind of train this like relightable hand model, taking a spatially varying lighting feature for better generalization and the incorporation of visibility so that it can generalize the novel light direction and the pulse combinations. Okay. All right. So now we have a solution for articulation. So what about the composition? So in a digital world, we are not only just a minimally closed human, right? We want to put the clothing, accessory, and so on. But to support the relighting together with those accessories, we have to account for this composability. So let's talk about that. This work is called the Megane, Morphable Eyeglass and Avatar Network, done together with my intern, Junshan. So this work was presented in CBPL this year. By the way, this megane literally means eyeglasses in Japanese, and that's why the abbreviation is megane in this work. All right, so what are the challenges to learning this, to learn a compositional glasses, which is also relightable? So there are a couple of challenges. So you may think, oh, glasses share the exact same template, and we can easily just interpolate between those two. But actually, it's not the case. You can see that in the middle, there's some glasses that has two bridges. So actually, the glasses do not share the single topology. It can actually change the topology as well. And what's more, it actually consists of various materials. Some glasses made of metal, and also like others are made of translucent plastics. So it has a completely different reflectance property, and in the traditional approach, it's really difficult to represent glasses with a single representation. So for that, we basically propose to leverage a flexible representation. For shape, to support topology change, we leverage a volumetric representation like NARF. In particular, we use our like a mixture of volumetric primitives because it's fast to render. And for appearance, similar to hand and the face, we also leverage the neural relighting. So instead of using a physically based relighting approach, we use a neural relighting to account for subsurface scattering, high refraction, and all those complex light transport effect. Okay. And another challenge is actually the interaction between accessory or like glasses and the face. So they are not actually like deforming and changing appearance independently, but they are actually affecting each other. The first is a contact. So like there's a contact point between like a face and the glasses, and that causes deformation on both sides. Okay, and also there's a non-local shading effect. So here, as you can see, the glass casts shadow on the face. And this is also like a highly nonlinear and complex based on the different light direction. And also by changing the facial expression, the glass moves slightly. So this kind of motion makes it difficult to also learn a static shape of glasses. And for that, we argue that the joint modeling is necessary. So instead of modeling face and glasses separately, let's observe them together to learn those mutual like interaction effect. More specifically, so this is a naive version of this composition of glasses. Let's say we have a glass decoder that can span different type of glasses through this latent called ZG, and we have that for our face as well. And this way, okay, if we know roughly where the glass is, we can just put them together in a 3D space, then render. However, this is not, as I said, accounting for this mutual interaction effect. So that if the deformation is not correctly modeled, maybe glass actually goes inside the head, and also the shadow and those like global light transport effect is not incorporated in this relighting results. So what we propose here is the interaction decoder. This basically models this interaction effect for both deformation and appearance change. And we add this residual of deformation and appearance change to each decoder to produce a final appearance. For the data set, we correct, I think, 24 subjects with and without glasses. For every person, we ask to wear different glasses, like up to 2 or 3. And they are making different facial expression with and without glasses. And what's more, all the captures are this like the relightable capture. So we can observe different light conditions for avatar as well. So here I show you the progress of how our glass geometry learns. As you can see, the glass shape and appearance emerge from the coarse initialization, which is just parameterize the plane to this through the volumetric inverse rendering. The leftmost is a ground truth image, and the second left is our rendering result after composition. As a result, we can build an interaction area generative model of glasses and heads. Now I interpolate latent code for face and the glass independently. So we can change glasses, but also identity. So here you can see that actually the model supported topology change. The glass changes the two bridge and the one bridge. This is not possible with a single mesh approach. So here I show the importance of our interaction area modeling. So let me show you the effect of our, the interaction layer. So here I flip between with and without our geometric interaction layer. As you can see, when the glass put on top of nodes, in reality, the nodes deforms, right? But if you don't account for this interaction, the glass goes inside the nodes. As you can see, without specifying what the deformation should be, our model automatically self-supervisory learn to produce this type of corrective through inverse rendering. So only the supervision signal here is the inverse rendering from images. Okay, so now we have a solution for geometry, and what about appearance? So we also introduced this interaction-aware neural relighting. Similar to our handwork, we also conditioned the appearance model with a shadow input. So this way, from this shadow input casted from the glass to the face, we can create a correct appearance effect, like a casting shadow with subsurface scattering effect on the face side. So here I show the aberration study of photometric interaction. I'm turning on and off this photometric interaction. This significantly improves the realism of like a virtual try-on of glasses. To be clear, on the right, this is our synthetic image. The face and the glasses are all learned model, not the real images. And this basically leads to our free relightable computational glass and the face avatar models. The results shows that the single generative model can support photorealistic relighting of a diverse frame material of glasses with accurate non-local shading effects on the avatars. So here you can see that on the glasses, it correctly modeled the reflection, like specular highlight, and the subsurface scattering in the middle. In the traditional, physics-based approach, it's really difficult to model this type of complex, scattering effect in a single model, single generative model. All right, and there's another cool thing about our representation. So our glass model is partially volumetric, but it still retains this correspondence through the polarimetric primitives. In a nutshell, it's basically representing volume as a composition of multiple small voxels. So that's why between different glasses, still it retains a correspondence. And what we can do is we can insert prescription lenses as an offline process. So we can semi-automatically detect where the lens should be, like as I show here on the red dot. And then, so we detect where the lens should be. And since the lens has a primary two effect, a reflection and a reflection, right? And given the shape of lenses, those effects are like uniquely determined. And what we do is when we shoot a ray, when we hit the glass surface, we just compute the two rays additionally for the refraction and the refraction, okay? So this way, even though we don't capture a subject with any like a precision lenses, we can still render avatar with a novel prescription. Here, as you can see, we can simulate like different near sight or far sight effect on the lenses. And here's our rendering results with a different also like a shading effect with the sunglasses. To be clear, none of those are real images, and the lens reflection is computed on the fly. All right, so let me briefly summarize what I have presented. So for the dynamic relighting capture, which is necessary for a digital human, we have to build and we have to develop a capture system and a data processing pipeline. The first key ingredient is a time multiplex group light. This allows us to address the cost of dimensionality, and with a limited reasonable time, we can still capture sufficient variation of combination of the pair of expression, right direction, and viewpoints. Also, to enable tracking, we propose to interleave free lit frames, and this way we can run a tracking on a free lit, but still interpolate for the remaining frame to learn a reasonable relighting appearance model. So another key takeaway is how can we achieve generalization? My go-to is to use correct inductive bias. So there are a couple of like a physical phenomenon in this relighting. For example, there's a linearity of light transport. Then like one way is to explicitly introduce this linearity of light transport in the learning process. Also, like we show that the physically based features, so there's certain things we know about physics, like, okay, shadow should be casted from this direction, reflection goes this direction based on the surface normal. So these things can be pre-computed as a feature and then feed it into the neural network. This improves the generalization of the network but also improves the fidelity. And what's more, like a compositionality is the key for the better generalization. And we want to achieve basically like a good like a generalization for the novel combination of, say, accessories, like different glasses and the faces. And for that, I argue that the representation need to be interaction aware, not only photorealistically, but also geometrically. This should account for the both deformation and the appearance change. Okay. So far, actually, this is not end of my talk. So far, I've been talking about the digital human modeling with light, which is visible, like basically an RGB domain. What about the digital human modeling with invisible light? Let me explain what I mean by that. So for hair 3D reconstruction, and this is a really notorious and super challenging problem, because I think the core problem here is the hair interior is never observable from the visible RGB domain. You can see the surface of hair, but you never see the interior structure of hair. This is especially challenging for curly hair, like I show under the left bottom. So in this, so we present our work in a SIGGRAPH this year called CT2 hair. So our key idea is let's see through it. So how? How can we see inside of hair? Our solution is to leverage X-ray. So X-ray can pass through most of objects except metal, and actually we can see through inside the hair structure. More specifically, we leverage computing tomography and let us see through inside of hair. So here's the density volume we get for hair. For those like the hair in data, which I show on the previous slide, basically I get this type of density volume. And it's very high quality, and it also has a correct interior information. You may think, okay, then the problem is solved. Actually, it's not really the case. Eventually, what we want is not only just a density volume, but a hair strand representation from top of from the root of the scalp to the tip of hair, right? This way, we can use a physically based like a rendering framework or physics-based simulation. Volumetric alone is not sufficient for this type of applications. So here's the problem. Like, it looks great, but if you zoom in, actually this density volume is very noisy. And this is kind of a fundamental limitation of a CT scanner. So the question is, how can we robustly build a hair strands from this noisy density volume? And in fact, if you apply a gobble filter, like classic, orientation estimation, it becomes very noisy and difficult to, rely on the prediction. And we basically propose a robust orientation estimation inspired by our a vector calculus, a tensor calculus. The key idea is always a hair at a tangential direction, and the density volume gradient direction is orthogonal. And we solve this as an eigenvector, eigenvalue decomposition problem. And this way, we can obtain much more accurate orientation information from this density volume. Comparing against the gobble filter, you can clearly see the improvement. And the left and right bottom, I show our reconstruction results versus gobble filter. This also leads to better reconstruction of hair strands. On top, we also propose a cost to fine optimization. So from this orientation assigned density volume, we specify it and then only extract the reliable hair strands and then do the filtering to only take the strands that comes from the root of scalp to the tip of hair. And then we do the interpolation and extra refinement process to get the final hair strand representation. So here I show you our final strand reconstruction result. As you can see, our approach can produce very realistic, plausible hair strands from a CT scan in a free automatic manner. There's no manual process involved, and it supports a wide range of hairstyles, which was not really possible with the prior approaches. So here I show you the comparison with the prior approaches. There are a couple of learning-based solutions, like neural HD hair or DeepMBS hair. And those definitely give us plausible hairs, but it's just plausible, not really accurate. If you zoom in, there are many local details missing and incorrect. And the second right image, we show that the comparison against a line-based multi-view stereo. This gives us a strand accurate reconstruction, but only for the visible area. It completely lacks the interior information. So like, as you can see from the image-based solution, this getting the accurate interior is very challenging. On the other hand, our approach can produce very realistic and accurate hair strands from the CT data. All right, so let me quickly summarize. So for the digital human modeling with light, not only like we can make the avatar relatable, but also we can see something that was not possible in the RGB visible domain. For example, X-ray lets you see through, so you can account for the occlusion problem. And we also propose a robust orientation estimation with a vector calculus and a cost-to-fine optimization for robust reconstruction. And what's most important is we release code, model, and the data. So if you're interested in this super high quality CT data of hair and building even better reconstruction algorithm, please check out our code and data. All right, so that's all for my presentation. Thanks for listening.
Okay, fantastic talk with super strong visual effects, actually. Thanks, Shunsuke, for the very detailed explanation of both the inherent theory and also the design philosophy of creating digital human with light. So I have a bunch of questions. So the first one is actually not everyone have the opportunity to get access to such advanced data. Actually, so do you think it is possible to use monocular camera? Actually, Professor Ju Yong, the first talk is talking about monocular camera-based human reconstruction. So do you think it is possible to use monocular camera with light or not to achieve also production level results if we can, for example, well utilize current advancement of AI, for example, diffusion models, foundation models, or something else? Yeah.
Yeah, it's a great question. So I think ultimately the answer is yes. But I think here, this like a kind of in the wild reconstruction, I also originally from this kind of background as well. I think requires good data player, as you mentioned. So this requires like good training data or the good observation. Like without knowing, like what the target is, it's really difficult to achieve this type of high quality results. That's why, like, so in my PhD, I'm more pushing from a limited input and then try to achieve the best quality as possible, like PyFH and stuff. And here in the reality lab, I'm kind of approaching from the other direction. Given the highest quality data, what's the best quality we can achieve, and then how we can reduce the input. Like ultimately, what we want to achieve is from, as you said, from minimal input, we want to achieve the best quality.
Yeah,
I think like we have to kind of like merge them together. We have to first collect high quality data, high quality like algorithm, and then like produce a bunch of data to learn a data player. And this definitely help us learn or like regress a high quality output from in the wild data. So I think we are in the middle of this journey and we still don't have a working solution for that. But down the road, I think this is certainly possible.
Okay. Yeah, I totally agree with you. And my second question is, I'm very interested in the mechanism work. So my little question is for the glass generator. When collecting the data, you need people to wear different glasses and do different extractions. So I was wondering how to, do you need to segment the glass from the head? And do you first reconstruction and then segmentation, or first segment the class in the image and then reconstruct the class independently?
Yeah, it's also a great question. So like for this work in particular, we basically try to leverage the best possible segmentation. So like we indeed run our image-based segmentation on the glasses, and that's consolidated in the form of our like non-rigid ICP. So like we basically first reconstruct the glass template for individual glasses, and then based on segmentation key points, those like annotation data we have, we basically try to first filter the glass geometry to ease the training process. But actually, there's a new ICCB paper this year I have, which is basically removing all those constraints. It's a bit different domain, but instead of taking this high quality segmentation and those annotation data, let's just have a two pair, with and without accessory. And those two set of just semantically separated capture is enough to separate the component? And then we found that the answer is yes. Well, we only did it for geometry. Like this is a collaboration with the Seoul National University, the Hanbyo, under his student Teksu. So if you are interested, please check it out. But as I said, for this work to achieve the best possible quality, we rely on this type of high quality annotation data. But down the road, I think all we need is like a semantically separated kind of a data. So like instead of just getting better annotation, but we can also add just extra label, like with and without accessory. In a natural, like in a semantic level, if you just subtract with accessory and without, you should be able to get just accessory alone, right? And together with like generative modeling, this seems to be feasible. So this is a very interesting and exciting direction, I believe.
Very interesting. I will definitely check this paper later. And my last question is, I noticed that you mentioned the MVP. It's very efficient volumetric representation for avatars. Recently there is also another work named Gaussian splitting. It's a little bit similar to the MVP. And can you? I was wondering, have you ever tried to use Gaussian splitting to replace MVP, or in your opinion, the difference between these two methods?
So we did some experiment with Gaussian splitting, and I think short answer is like Gaussian splitting can be be a bit more efficient, like primarily because the Gaussian splitting relies on rasterization, whereas the MVP still relies on the ray marching. So for the ray marching, we first have to know, like which voxel intersect and then aggregate around the ray. And rasterization is actually blazingly fast, and the couple of implementation difference, more or less like they can achieve the same quality. And the one thing to note is Gaussian splitting seems to be is actually good at representing like a thin structure. Like in the original paper in Gaussian splitting, they showed that the spike of a bike tire was really well reconstructed, which is pretty difficult with other volumetric approaches. So there's kind of pros and cons, but the generally there's some unique advantages of Gaussian splitting, and I think they should co-evolve. Like it doesn't necessarily mean MVP is not useful anymore. I think it still has its like a use case, but I think that leveraging this type of more point-based representation in a generative modeling seems to be a very exciting and interesting direction.
Yeah, of course. Totally agree with you. So that's all for all of my questions, and due to time limit, we will end that here. So thanks, Shunsuke, again for the fantastic talk, and thanks all the audience, and see you next time.